When most people hear the words black hole, they imagine a giant empty hole in space like a cosmic drain pulling everything in. But that picture is misleading. A black hole is not an empty hole. It is an object, a real physical region of space where matter has collapsed into such an extreme state that gravity becomes unbelievably powerful. If our sun became a black hole, it would not suddenly start sucking Earth in like a vacuum cleaner. Earth would keep orbiting almost the same way as it does now, because gravity depends on mass, not on whether the object is a star or a black hole. So what makes a black hole special is not that it has extra gravity, but that the same mass is packed into an incredibly small volume. This makes the gravitational field near it so steep that escape becomes impossible once you get too close. This is the first important mystery. How can gravity become so strong that even light cannot escape? To understand that, we need to understand something even stranger. A black hole doesn't just bend space, it bends time too. Every black hole has a boundary called the event horizon. This is not a physical wall. It is not a surface you can touch. It is simply a region in space where the escape speed becomes greater than the speed of light. For example, to escape Earth's gravity, a rocket must travel about 11.2 kilometers per second. That's Earth's escape velocity. For a black hole, the escape velocity at the event horizon is equal to the speed of light. And because nothing can travel faster than light, nothing can escape once it crosses that boundary. This is why black holes are black. Not because they are made of dark material, but because light cannot get out. Now here's where it gets truly mind-blowing. If you were far away watching someone fall toward a black hole, you would see them slow down as they approach the event horizon. Their movement would appear to become slower and slower, almost like time is freezing. But the person falling in would not feel that freezing. From their perspective, they cross the event horizon normally. This is not science fiction. This is a real prediction of Einstein's theory of relativity. So the event horizon is not only a point of no return. It is also a place where time becomes strange. One of the biggest misconceptions is that black holes are invisible. Technically, the black hole itself is invisible, yes. But the region around it can be extremely bright. In fact, some of the brightest objects in the universe are powered by black holes. When gas, dust, or even stars fall toward a black hole, they don't fall straight in. They usually spiral, forming a swirling disk called an accretion disk. As matter spins faster and faster, friction and pressure heat it up to millions of degrees. It begins to glow intensely, producing X-rays, gamma rays, radio waves, visible light. So ironically, black holes are often detected not by darkness, but by extreme brightness. And in 2019, humanity captured the first direct image of a black hole's shadow, a glowing ring with a dark center. That image did not show the black hole itself. It showed the event horizon's effect on light. And that is a clue to the deeper mystery. Black holes don't just swallow matter. They swallow information. Now we reach the real question. When something falls into a black hole, what happens to it? The simple answer is, it gets pulled in and eventually reaches the center. But the real answer is far more disturbing. Because near a black hole, gravity becomes uneven. The closer you get, the stronger gravity becomes. This creates something called tidal forces. Tidal forces are the same kind of force that creates ocean tides on Earth, because the moon pulls more strongly on the side of Earth closest to it. But near a black hole, tidal forces are extreme. If you were falling feet first, gravity would pull your feet much harder than your head. You would be stretched longer and longer. This is not a joke, physicists call it spaghettification. Your body would be stretched into a long thin stream of atoms. For small black holes, you would be torn apart before you even reach the event horizon. For supermassive black holes, like the one in the center of our galaxy, the tidal forces at the event horizon are weaker, meaning you could cross the horizon first, and only later be destroyed deeper inside. And this leads us to the terrifying truth. Once you cross the event horizon, there is no coming back. No message. No signal. No light. Nothing. But the biggest mystery is not about death. The biggest mystery is, does anything actually reach the center? Or does physics break before that happens? That is what we explore in part 2. One of the strangest truths about black holes is this. If the black hole is large enough, you may cross the event horizon without feeling anything special at that moment. There is no wall. No explosion. No magical barrier. From your perspective, you're simply falling. But the moment you cross the event horizon, something fundamental changes in the structure of reality. Outside a black hole, you can choose your direction. Forward, backward, left, right, up, down. And you can also choose to accelerate away from the black hole if you have enough fuel. But inside the event horizon, your choices disappear. The reason is not that a force is pulling you like a rope. The reason is that space and time are warped so severely that the center of the black hole becomes as unavoidable as the future. In normal life, you can't stop time. You can't decide not to go into tomorrow. Inside the event horizon, you can't decide not to go toward the center. That's not poetry. That's literally what Einstein's equations predict. This is one of the most important concepts in black hole physics, and it sounds impossible at first. Outside the black hole, time flows forward. Space is something you move through. Inside the black hole, the direction toward the singularity becomes like time. It becomes your unavoidable future. In other words, falling toward the center is no longer a choice. Even if you had a powerful rocket, you could not turn around and escape, because all possible paths forward lead inward. It's like being on a road where every direction leads to the same destination. The singularity becomes inevitable. This is why black holes are not just strong gravity wells. They are regions where the geometry of spacetime becomes one way. This is the first reason black holes are considered the most extreme objects in the universe. But the deeper you fall, the more bizarre reality becomes. To understand how strange this is, let's talk about light. Light normally travels in straight lines through space. But gravity bends space. So near a black hole, light bends too. Outside the event horizon, light can still escape if it travels in the right direction. But at the event horizon, light is trapped. Inside the event horizon, all light paths curve inward. Even a flashlight pointed outward cannot send light out. This is not because light becomes slower. Light always moves at the same speed locally. The problem is, space itself is so curved that outward no longer leads outward. It leads deeper in. This is why physicists sometimes say, inside a black hole, the singularity is not a place, it is a moment. And that brings us to a disturbing thought. If space and time behave differently inside, what happens to the laws of physics? Do atoms still exist? Do particles behave normally? Does the concept of matter even remain meaningful? At the center of a black hole, Einstein's equations predict a singularity. A singularity is a point where density becomes infinite. Gravity becomes infinite. Space-time curvature becomes infinite. But in physics, the word infinite is a warning sign. It usually means our theory has reached a breaking point. For example, in classical physics, if you calculate what happens inside an atom, you also get infinities. But quantum mechanics fixes that. So most physicists do not believe the singularity is literally an infinite point. Instead, they believe it is where general relativity stops working, and a deeper theory is needed. That deeper theory would combine general relativity, gravity, with quantum mechanics, the physics of the very small. This missing theory is often called quantum gravity. And this is one of the biggest unsolved problems in all of science. So the real mystery inside black holes is not just what happens when you fall in. The bigger mystery is, what is the center really made of? And does the universe allow infinite density at all? Now we are ready for the most famous paradox of black holes, a problem so serious that it has confused the greatest physicists for decades. In part 3, we explore. To understand why black holes are so mysterious, we need to understand a rule that physics strongly believes is true. White heavy checkmark information cannot be destroyed. This idea comes from quantum mechanics. In simple words, information means the exact details of a system, the arrangement of particles, the properties that define what something is. For example, if you burn a book, the book turns into ash, smoke, and heat. The book is destroyed, but physics says the information is not truly gone. In theory, if you could measure every particle and every bit of energy perfectly, you could reconstruct what happened. This is why physicists say the universe is like a giant record keeper. Even if something changes form, the information is still preserved. Now here's the problem. A black hole seems to break that rule. Imagine you throw different things into a black hole. A gold bar, a diamond, a book, a smartphone, a human, an entire planet. From the outside, the black hole doesn't show you what fell in. According to the simplest description, a black hole is defined only by 1. Mass. 2. Electric charge. 3. Spin, rotation. That's it. This idea is sometimes called black holes have no hair, meaning they have no visible details. So if you throw a book into a black hole, and then throw a diamond into the same black hole, the outside world cannot tell the difference. But that seems impossible. Because in quantum mechanics, those differences are information. So where did the information go? In the 1970s, physicist Stephen Hawking discovered something shocking. He showed that black holes may not be completely black. They may slowly emit tiny amounts of energy, now called Hawking radiation. This happens because of quantum effects near the event horizon. In quantum physics, empty space is not truly empty. It constantly produces pairs of particles and antiparticles that appear briefly, then disappear. Near the event horizon, one particle can fall in while the other escapes. To an outside observer, it looks like the black hole is emitting radiation. This means black holes slowly lose mass. Over extremely long time periods, they can evaporate. Now here comes the terrifying part. If a black hole evaporates completely, then everything that fell in is gone. And if the information is gone, then the universe has lost information. That would break the foundations of quantum physics. This is not a small issue. This is a major crisis in physics. Because it suggests that either quantum mechanics is wrong, or our understanding of black holes is incomplete. So scientists asked a critical question. If information is not destroyed, where is it? One possible answer is the information is somehow stored on the event horizon itself. This idea led to one of the most mind-blowing concepts in modern physics: the holographic principle. This principle suggests that all the information inside a region of space might be encoded on its boundary like a hologram. In black holes, it would mean everything that falls in gets recorded on the surface of the event horizon. Even more shocking, some theories suggest the universe itself may behave like a hologram where reality inside space is encoded on a cosmic boundary. But this leads to another problem. If the horizon stores information, then something must happen to the person falling in. Because the person falling in believes, I crossed the horizon smoothly. But the outside universe might say, no, the horizon is a kind of information barrier. To solve the paradox, some physicists proposed something extreme: the firewall hypothesis. This idea says, instead of crossing smoothly, the event horizon might contain a violent wall of energy, a firewall, that destroys anything instantly. That would solve the information problem, because the information would never truly enter the black hole. But it creates a new problem. It breaks Einstein's prediction that the horizon should feel normal for a falling observer. So black holes have created a battle between two giants: Einstein's general relativity, quantum mechanics. And both theories work perfectly in their own domains. But inside a black hole, they clash. This is why black holes are considered the greatest laboratory in nature for testing reality. In part 4, we reach the final and deepest question. Is there something beyond the black hole? Wormholes, other universes, and what the future of physics might reveal. One of the most common questions people ask is, if black holes trap everything, where does it all go? And that leads to the most famous science fiction idea. Black holes are portals to other universes. This idea is not completely random. It comes from real mathematics in general relativity. Einstein's equations allow strange solutions called wormholes. Einstein-Rosen bridges. A wormhole is like a tunnel connecting two distant points in space or even two different universes. In theory, a black hole could be one end of such a tunnel. But there is a big problem. Most wormhole solutions are unstable. They collapse instantly before anything can travel through them. And many require something called exotic matter, a form of matter with negative energy density. We have no evidence that exotic matter exists in a usable form. So while wormholes are mathematically possible, there is no proof that real black holes are safe tunnels. The honest scientific answer is, white heavy checkmark black holes could possibly connect to something else. Crossmark, but there is no evidence, and no known way to survive the trip. Here is another mystery most people don't realize. Black holes are not only hard to enter, they are hard to even understand because no information comes out. That means we cannot directly observe what happens inside. Everything we know comes from mathematics, simulations, indirect observations, like X-rays from accretion disks. This makes black holes unique in science. Normally, science progresses by experiments. But black holes are like a locked room in the universe. We can study the door. We can study the shadows. We can study the light around it. But the inside remains hidden. This is why black holes represent the edge of human knowledge. Many physicists believe black holes are not just objects. They are clues. They might be nature's way of showing us that our current physics is incomplete. Because inside a black hole, two powerful theories collide. General relativity describes gravity, describes large-scale space and time. Quantum mechanics describes particles, describes the microscopic world. Both are correct. Both are tested. Both are incredibly accurate. But they cannot both be fully correct in a black hole. And this tells us something profound. Reality is deeper than our current understanding. Some physicists believe that when we finally discover a working theory of quantum gravity, we will understand what happens at the singularity. What happens to information? Whether the horizon is smooth or violent. Whether black holes truly evaporate. And possibly, we may discover that the universe is not what we think it is. So what is the real mystery inside black holes? It is not just that they are powerful. It is not just that they trap light. It is not even that time slows down. The real mystery is this. Black holes challenge the rules of reality. They force us to ask questions like, can information be destroyed? Can time and space swap roles? Does the universe allow infinite density? What happens when physics reaches its limits? A black hole is where the universe hides its deepest secrets. And what makes this even more mind-blowing is, black holes are not rare. There may be millions in our galaxy, billions across the universe. Some are small. Some are supermassive. And some may have existed since the early universe. And every one of them is a cosmic message. A reminder that our understanding of reality is still incomplete. So when you look at a black hole, you are not just looking at a dark object. You are looking at a boundary between what we know and what we still don't understand. And maybe, the greatest discoveries of the future will not come from faraway galaxies, but from solving the mystery of what happens inside a black hole.
Subscribe Info Beyond Borders now for more mind-blowing knowledge.